Well, hello. This is the start of Chapter 10. Chapter 10 for Hooke Physics is entitled Periodic Motion. And this starts on page 317. And what we call periodic motion is something that actually all of us experience practically every day, but we probably take it for granted. It could be as simple as a wheel going around and around. That's periodic motion. In other words, motion that's periodic. It has a certain period to it, and it repeats itself. The very simple example would be when you ride your bicycle, your wheel goes round and round and round. It goes around with a certain period to it that may increase or decrease, but that's periodic motion. There's all kinds of types of periodic motion. If you see a tree limb blowing in the breeze, it goes back and forth and back and forth. That's periodic motion. The motion repeats itself, and it has a certain period to it. That's a certain length of time from the limb being down to the limb being up and then back down. So the period of motion, the motion of the limb or the motion of a tree has a certain period to it. And so there's many things in the physical realm that we look at that naturally we describe have a motion to it, but this motion is back and forth like a seesaw. And so it's not linear motion, but it's back and forth motion, which we call periodic motion. Now, to help us describe this, we're first going to look at springs. Springs, just like this spring, actually, this is a slinky. You all are probably familiar with this, maybe. Slinkies are wonderful, fun toys to play with. I recommend you highly you get one. They're fun, and just for playing with it. But they also demonstrate many nice principles of springs and waves, which we'll talk about in Chapter 11. And so, but a slinky, essentially, at the heart of a slinky, or what is a slinky? It's a spring. And if I let's see here, if I pull it down, it comes back up, and so there we can have periodic motion there. If I pull down harder, if I were to attach a weight to it, it would pull down. If I would make the weight heavier, it would pull down even further. Okay. Springs have a natural tendency to actually restore themselves. That is, the spring has a natural tendency to restore itself back to an original shape. If I pull the spring down and then I let it go, it has a natural tendency to pull back into its original shape. Let's see. For instance, if I let that length of string just dangle, we would say essentially that's the original shape. If I push up on it, it wants to go down to its original shape. If I pull down on it, it wants to go up to its original shape. So the spring has a tendency to always want to get back to its natural state. This natural state being the state that is described by an equilibrium condition. Okay, whereas the weight hanging down is equal to some kind of spring force that's pulling it back up. Okay, so this spring force that wants to pull the spring back up, we call a restoring force. A restoring force because it wants to restore the force. It's a restoring force that wants to restore the spring back to its natural shape. What is the natural shape? The natural shape is the shape that it has at an equilibrium static condition. Okay? So What I have described here is actually in Chapter 10, but it's described over the course of the first probably 6 to 8 pages, but just in a very hopefully easy to understand language. But let's first go over Hooke's law. Robert Hooke was an English scientist, and Hooke's law is a very, very easy law to understand, but it's amazing how widely used this is. And it starts on page 317, and it in fact continues for, to about 323. Hooke's law is a very easy law, and it simply goes like this. The restoring force of a spring, okay, is equal to, we'll call that F, and I'll put F sub restore. Restoring, it's a restoring force. That's equal to minus K delta X. Okay, this is a very easy law. Turns out that for those of you who go into science fields like physics or engineering especially, you will see Hooke's law used not only for springs, which is what we're going to use it for, but for a wide variety of applications. This Hooke's law is used in engineering quite often to talk about, for instance, if you study beams, how much does a beam bend? If you have a beam of steel or wood and you want to put a force in here, the beam tends to deflect a certain amount of distance. And to the first approximation, the way to describe it is using Hooke's law. Okay, so Hooke's law is used a lot in engineering. Hooke's law turns out is used for big things, but it's also used for very minute little things. There's even some, when you deal with even things like atomic physics, and you look at the physics of the atom and the nucleus of an atom, some of the forces involved are actually modeled using a law that's essentially Hooke's law. It's a very simple model, but it's used for a wide variety of applications. Well, how do we apply this to springs? If we set a spring, and you can look at some diagrams, for instance, on page 318, they have an example diagram. Probably the best diagram of this is on page 322. For example, 10.1. If I have a spring, and this is like a ceiling, and I have a spring here, and here's my spring, okay, and I attach a weight to it. Well, first of all, let's just put the spring like this. If the spring is, suppose this is a spring, and this represents a spring, okay. The spring naturally has just its own weight to it, okay, so it hangs down. But if I attach a weight to it, we'll say a mass M, okay, that will tend to elongate the spring just a little bit, or maybe a lot. It will elongate the spring. And so let's assume, I'm going to assume right now that I have a weight on this spring. Actually, there's no real weight hanging on the spring, but I'm just using the weight of the spring itself to pull itself down. Okay, so it would be like I have a weight on this spring, and this spring will tend to come to a certain distance. So what I'm going to do is I'm going to say, I'm going to have this weight with a certain marker right here. And this arrow, okay, is going to point to a ruler. And I have a ruler, here, just like this ruler here. I have a ruler here, and I set the ruler up, okay, and I can measure. If I add more weight, the spring comes down, the spring elongates. I can measure the distance. Okay, so if I take the spring and I let it come to an equilibrium, I'm going to imagine that this point right here represents this point. I wait until all the oscillations are gone. Okay, this point becomes what I'm going to call the equilibrium point, and I'm going to have a measurement right where that point is. So the spring itself will naturally, with a particular weight, will naturally have a certain equilibrium position. Equilibrium position. Okay. And now what will happen is if I add more weight, and well, what I'm going to say is that this equilibrium position is valid for a certain spring configuration. And in this case, the spring configuration would be for this particular arrangement that I've set up here. Now, if I add weight to this, say I add a weight M1 to this, so this will be the original M plus M1, I'll call it M1, okay. The spring naturally elongates. Well, let's see. That's M, and I add a weight M1. This spring naturally elongates down to here. And this is, I'll call this delta X1. Okay? And I can measure that distance in centimeters or inches or something like that. Now, if I add another weight, say I add M2, which is greater than M1, this spring will elongate again, this time all the way down here, and I'll call this delta X2. Okay, so what we find is that if I make a chart, and what I'm going to say is the weight I add to this, for instance, I'm adding the original mass here is M. What I've added here, the weight is weight 1, which is M1G. The weight is the mass times gravitational attraction. The added weight that I've added here is W2 of M2G. That's what's been added. Okay? So I can call this added weight, I'm going to call that force 1. And I'm going to call this force 2. So force 1 is where I've added a certain weight, M1, times, and I multiply it by G. Then force 2 is M2 times G. Okay? So I come over here, and on this axis I'm going to plot delta X, and on this axis I'm going to plot the y-axis. I'm going to call this the added force. Okay, that is F1 and F2. Now notice, when I've added nothing, I've added 0 force or mass to this. There's a 0 here. I'm at my equilibrium position where delta X equals 0. So I have a point here where there's 0 on delta X, but there's 0 on the force added. Then I come over here, and I have this point here. I add a certain F1 force. Here's, say, F1 charts right here. And the spring elongates a certain delta x1, and I'll call that delta x1. Okay, and that plots out a point right here, and I plot that point. Okay. Then I plot the next point over here, F2. Suppose here's F2, and I'm just using variables here. I'm not using numbers. And the coordinate for x, the x coordinate for this force is the delta x2, which I'm going to say is down here, delta x2. Okay, so notice that I'm plotting the coordinates of these points. This is x, y, and here the first coordinate is delta x1, and the first coordinate here is the force, F1, that I've added, is the force that I've added to the spring. And the second one over here, the second point that I'm plotting is delta x2 and F2. Okay, these are points that I'm adding. Then I take my straight edge, and what I notice is that if I plot many of these points, they fall along, or they tend to fall along, a straight line. Okay, in fact, I'm going to draw a straight line along here. Whoops. Okay. And I'm in my model, what is my mathematical model that I'm going to put according to model this data has this, it's a straight line with a slope, and I'm going to call the slope K. Now you remember from algebra how to do this. This equation for this line would be y. Well, if you think of the slope as m, like in algebra often we do, the slope of this equation will be y equals mx, or delta x. X is delta x, or y equal mx. Now, in this case, my y is the force. The slope here is k. I'm going to call it just k. And the x-axis is delta x. Okay, and this is exactly Hooke's law. Hooke's law is the force is equal to minus k delta x. Okay, now there's no, notice, well, first of all, there is a minus sign, but right now we'll ignore the minus sign. This Hooke's law simply states that there's a linear relationship when I add weights to this, or add forces to the spring elongates a certain distance. The higher the force, the higher the spring stretches. Okay, and if you plot many points, it would follow along a straight line. Now, is this a perfect law? Well, it's perfect in as much as we observe it to be true empirically. Now, what actually happens if we would take an actual spring, and we kept on pulling it, what would happen? We would actually pull it so hard we would start to unnaturally elongate the spring, and we would start taking the springiness out of the spring. If we pulled it far enough, the spring will not restore itself. Essentially, we have destroyed some of the inner memory of the working metal. And this is what happens if this Hooke's law only operates, I don't think the book talks about this, but in engineering we talk about this. The Hooke's law only operates only a certain range. If you keep on adding more and more force, eventually this levels out. It goes, as we call, non-linear. It goes into a range where we have bent out essentially all the restoring force of the spring, and at some point, if we keep on adding more force, we can do irreparable damage to the spring. It's just like if you have a beam in engineering, you have a end supported beam, you start adding weight to this. Notice this beam starts to bend in a linear fashion, but if we put so much weight on this, it starts to bend a lot. I'm not going to break it, but if I've added enough weight to this, I would actually break the beam, I would break the meter stick, and I've essentially destroyed, I've done irreparable damage to the material that I was testing. Okay, so Hooke's law is a valid law, but it's only valid over a limited range of extension. Okay, so that's an important point. Okay, well, let's examine this. But this is Hooke's law. What I'm going to do now is examine this from a slightly different point of view. Let's examine this from the point of view of what the spring is actually feeling. Okay? Okay, from the point of view of this of the spring, let's add a certain weight to this. So the spring is extended down to this point here. I'm going to erase this one. Okay, so we've added weight M1, so we're down to here with the added force is F1. The spring has extended down to this point. At this point, let's draw what we've called in chapters before. Let's draw a free body diagram of the spring weight system. Okay, essentially at that point what we have, again, here's the ceiling. We have the spring. The spring has elongated all the way down to here. Okay, we've elongated. That's about right. The spring is stretched out, and this point is right here. Okay. Now let's draw a force diagram. What are the forces acting on this mass? In this case, the mass M plus M1. Okay. What are the forces acting on the spring? Okay. What we have is we have the weight. In this case, what I'm going to do now is I'm only going to talk about the added weight, the M1. Okay, I'm only going to talk about the added weight. Let's assume, just to make the argument simple, I'm going to assume that the original mass to get up to this point is 0. So let's assume that there's no mass added at this point. Okay, and when we add a mass, it's that the spring naturally is right here with no added mass, and now we add a certain mass to it, M1, and it stretches down to here. Okay, this will just make the concept a little bit easier to understand. Okay, let's draw a free body diagram. The free body diagram looks like this. We draw the mass. Here's the mass M1. What is the force acting down? The force that's acting down is the weight. The weight equals M1G. Okay. Well, this weight here, this mass here, is stationary. It's not going up. It's not going down. It's not accelerating. So if something is caught in midair, we know gravity acts down. There must be another force acting up to keep this position, to keep the mass at the same position. And there is. Weight acts down, but there's another force acting up, and we call this the restoring force, the spring restoring force. Okay? Now, how large is that restoring force? Well, we know exactly how large is the restoring force because we know that the sum of the forces acting on the system is 0. Okay? Acting up, we have this restoring force. That acts up, and acting down is the weight, m1g. Okay, so this means, and this is equal to 0. So we know that the restoring force is equal to m1g. Okay, now from Hooke's law, okay, we also know that the restoring force is minus k delta x. Okay, now minus k delta x. Now k is that spring constant. K is a slope. K, remember, we have this is delta x, and this is the restoring force, and then we have this k. This k, the slope of this line is k. We call k the spring constant. It's a constant, and it's a constant associated with the spring. We simply call it the spring constant. Okay. Now, the weight in this case is acting down. The weight is acting down. This force acts down. The restoring force has to act up in order to compensate for it. Okay. Notice that in delta x here, notice if we say delta x is a vector, notice that the vector acts down. The minus kx, the minus sign indicates the direction of the restoring force. If this vector acts, if the delta x vector acts down, it's a downward pointing vector, then the restoring force, being negative that, must act up. In other words, the minus sign indicates that the restoring force acts in the opposite direction of the elongation of the spring. Okay? So, we can also say, let me erase this. If we have a system, a spring system that is, and our equilibrium position is right here, and then we push delta x up this way, so that now the spring is compressed from here to here. So delta x, let's say up is positive. If delta x is positive here, if delta x is going up, then minus k delta x is the restoring force. So the restoring force, if delta x is plus, the restoring force must have a negative sign to it, and it must act in the opposite direction. The restoring force must act down, and in fact it does. If here's my natural equilibrium position, and I push up on the spring, there's a force that generated internally to the spring that pushes it back down. Okay? So the restoring force acts in the opposite direction of whatever the elongation is. If I pull down, that is I elongate it down, the restoring force acts up. if I push the spring up, the restoring force acts down. Okay, so that's the whole point to this negative sign. Okay. Now, let's see here. Let me just do a quick little example. For instance, if you have a okay, if I have a spring here, and here's the equilibrium position, and I add a certain weight to this, we'll say 25 grams. I add a 25-gram weight, and when I do that, this elongates down from the equilibrium position to, I'm looking at on your own problem on page 323, it elongates 3.45 centimeters. Okay, what is the